Thank you very much. So the topic today about solid state thermionic energy conversion for waste heat recovery. And basically I will start with a motivation about our energy usage and what is the role of the waste heat. I will talk about some of the fundamental thermoelectric effects, interaction of heat and electricity, and then I will talk about what is practical applications of thermoelectrics right now, some of the more work on the atomic level and the microscopic origin of thermoelectrics, and what advances has been done in the last 5 to 10 years. So it's a good starting point to see how energy flow in US have changed. And this is a diagram, it's sometimes called the spaghetti diagrams, so it's appropriate for lunch meetings. It's developed by Lawrence Livermore about the data that is provided by the Department of Energy. It tells you energy sources on the left, and on the right you see where the energies are consumed. And you see in 1950, about 32 quadrillion British thermal units were used. It's very strange units. You just add 20% to it, it becomes ettajoules. I don't know if it helps to anything that you want to say. At that time, coal and petroleum was big sources of energy. A lot of it was internal. Import of the petroleum was little, and hydraulic is there and natural gas. This is electricity generation, and then three main applications: residential and commercial, industrial, and transportation. If you look at it, you see that what is the useful amount of energy and what is waste is about half of the energy that was coming into US was basically waste. Yes?
How much energy was generated from the nuclear energy at that time?
Oh, zero. 1950, that was just beginning of the nuclear time. So now if we switch on to 2002, 50 years later, well, there is good things about PowerPoints. The graphs are much nicer. So you could see now that the total consumption is tripled comparing to that time, about 90 quad. Population of the US is almost, it's not even doubled. So definitely per capita we have increased the consumption. And you see that there is a significant fraction of the oil which is imported. And from that you can get a lot of conclusions about things that is happening around us. Coal is still a major source, but is mainly used for electricity generation in power plants. Natural gas, nuclear is here, so it's also big fractions, and this electric sources and biomass is here. What you realize is that the three main applications stay the same, but transportation have grown significantly comparing to the other two. And in addition, overall efficiency have decreased from 49% to 61%. And well, that's not good. That means that we are not using our energy efficiently. If you look at it in this graph, so as I said, transportation energy between 1950s and today have significantly increased, more than factor of 3, is almost exclusively petroleum. And you know, in a car that you drive, that's not a very efficient transfer of energy from chemical to mechanical. 2/3 of the power in the car is dissipated in form of heat, typically 1/3 of it in the engine that heats up to about 1,000 degrees Celsius, another third of it goes through the exhaust catalytic converter, heats up to about 500-600 degrees Celsius. And there have been a lot of work, I guess, in the area of automobile since beginning of the 20th century, but that efficiency has not increased substantially. The recent work, I guess you all have heard about hybrid engines and how by combining an electric motor and a regular diesel type, you can get the fuel efficiency higher. But many of you have driven the hybrid cars. You know that it's not that the order of magnitude improvement that you get. And how far this could be pushed is also a question. If you look at it in terms of the residential and commercial, between 1950s and today, significant increase in the use of electricity. Why? Well, it makes sense. It's cleaner in the cities, and if you put the power plants far from cities, that alleviates some of the city environmental issues. But because electricity generation is not an efficient process, look at the amount of losses, that how much has increased over the years. Today you hear a lot of talks about renewable energies and candidates from solar to biomass, wind, geothermal, hydraulic, and so on. And you can probably take many courses here and other places about what are the trade-off in any of these sources. A question that could be interesting is that if we implement this renewable sources, how does it change the whole economy and the energy usage that we have? And Lawrence Livermore, they do studies of the projections. So they have a projection for US energy flow in 2050, 44 years from now, and they use a hydrogen economy, and 50% of the hydrogen is produced from renewable sources, and this is the projections they have. First of all, still have a big portion of the oil, which is going to the transportation. You see solar starts to have some decimals there, but it's a significant portion of wind for generation of electricity, which is also used for hydrogen production. And this is what the estimates are. But if you look at it, well, we have improved. In that case, the reject energy is 45%. If all of this is successful, and I think they have an assumption of about 80 miles per gallon kind of fuel economy in cars. As you see, even if the renewable sources become competitive in price, it's not, you don't see order of magnitude differences, and that's kind of a lesson comparing to information technology. If you compare 1950s to now, there is almost no comparisons. The amount of computation, the amount of communication we do is many orders of magnitude better, and a lot of predictions are based on how this could be continued. But in the area of energy, we don't have that much room to play. Improving energy efficiencies is difficult, and we should learn from history. If you look at airplanes, these are kind of really creatures of the 20th century. Between 1900 to 1950, speed of the airplanes were growing up, and you can find some graphs. They fit it with exponentials, and they say by this year you could travel between New York and Los Angeles in 2 hours, and you can have your lunch there and breakfast, or vice versa. And a lot of magazines, Popular Science magazine, 1950s, they were all proposing that this airline industry will keep improving. But if you look at it between 1950 and now, commercial airplanes are traveling at the same speed. There have been, of course, demonstration of going much faster. So technologically it's possible, but we are going the same speed. Why is that? Is the energy efficiency. You can go faster, but the friction increases with velocity square and limits in cube, and you have to pay much more for your travel. So at some point, people felt comfortable with the speed that they were going. You may think, well, we are not going as fast, but probably our technology have advanced so much, our airplanes are more efficient. We transport, we send more material through air, and we can send more material with less energy. In the same article in 2002, they look at the productivity index versus year, and this is basically the speed normalized by how much useful load they could carry divided by the total weight of the airplane. And that's an indication of how the material science have improved, and if per unit volume or unit mass of the airplane, we can transport more material, not faster. And you see Boeing 707 is almost the same as 777. So the big improvement there is definitely in the entertainment system. You have the TV monitors, individual TV monitors, and I guess people have given up. If you look at it in 1960s, they started the early 70s, the Concorde, the supersonic. and they went bankrupt. There is now here discussions about another sonic cruiser, and we will see if that will ever materialize. But if you talk to many people in technology, if you ask in year 2050 how we are traveling, how fast, they don't really predict significant changes comparing to the scenario we have today. So we have a lesson to learn, is that it's not that people like to sit in the airplanes for 10 hours, but at some point this is the cost, and we all deal with it. So if you look at in the amount of energy that is consumed in US, as I mentioned, the population increased, but also the energy consumed per capita have increased quite a bit. In 1950, the energy consumed in this million BTU unit was about 215, and in only 25 years, it's increased by 50%. And that's the time that a lot of facilities were provided in terms of the having more comfortable houses and comfortable transportation. That's where a lot of air conditionings were added and so on. And that's a huge change. If you look at this graph, you say, well, we haven't done that bad since 1980s. It stays flat per capita. But don't forget that we are staying flat as a very high maximum. US consumes, depending on different numbers, 1/4 to 1/5 of the total energy produced in the world. And we definitely don't have that much population. So it's a very high state that we are staying. And there was an interesting graph a couple of years ago. They compared daily energy consumption historically. And they started from a primitive man up to hunting period, primitive agriculture, advanced agriculture, industrial period, and today, I guess they call it technological. You see the energy at the beginning was only for the food. Well, I guess primitive man were quite healthy, 2 kilocalories, 2,000 kilocalories, which is 2,000 food calories is what I guess a healthy person should have per day. As we go on, in addition to the food, we have to have energy for our homes, and you see how much this have increased. This is basically the comfort we have to heat up and cool down our houses. Industry and agriculture, transportation is another big increase. It's interesting, when you look at this graph, you see for our food, today, the amount of energy is 5 times more than for primitive man. Do you think we eat 5 times more?
Tastes better.
Tastes better.
To what degree is, like, as you get more energy, is there more waste that someone forgets to leave on the lights when you have lights? As air conditioning on when you don't need the air conditioning?
More meat. We feed the meat, feed the cattle.
So let me answer both of them. So first of all, here is the energy that is necessary for the food product. If we refrigerate the foods or if we bring them from South America, all the transportation addition that goes to the food. So the way they calculate it here is basically in your food how much energy goes in producing it. In the early periods, you just look at what is the nearest tree, and you didn't have to put too much energy for it. This is all per capita or approximate numbers. I haven't seen numbers that what is consumed per capita, how much of it could be easily reduced by measures of conservations. But there have been data on overall kind of energy consumes that in the society how they have increased, and that's what you have seen it. But I haven't seen detailed analysis quantitatively. Well, I guess that was a long introduction to tell you that we have major energy losses in our society, 2 main areas, transportation and electricity generation. And both of these, for engines and power plants, have been around for some time. We don't expect significant changes in the efficiency of those cases. So the question is, can we do anything with the waste heat? That's 60% of the energy that is just going into nothing. Yes?
What about transmission of electricity?
Transmission of electricity at high voltages, I don't exactly remember, but is almost 93% efficient. It's interesting that you bring that question is early on in the discussions with superconductivity and high temperature superconductor, the idea was that will suddenly improve our energy efficiency significantly. It's not in the area of transmission. Every wire has an electrical resistance, but when you go to thousands of volts for long haul transmission, the losses are quite minimal. But I guess there is something to gain there. Yes.
So if we all had cars that we plugged into the wall, would it be a 10% net improvement?
That's actually a good question, is that if you look at it, the energy efficiency of the cars, electrical cars comparing to the kind of diesel engines, definitely on the electrical cars is better. The main reason is how you accelerate and decelerate. But I haven't seen a clear analysis. But just to give you an idea, typically our best power plants have an efficiency of about 50%. And you have all these issues. Most of our loss in the electricity is not is at the generation and not in the transport, but also in the storage, because we don't use it all the time, the uniform amount. That's a huge cost to store it. And the cars are about 20 to 30% efficient. So there is somewhere there that you could gain, but it's not a huge gain that you can have. So let me now go to the main part of it. What can we do with the heat? Can we generate electricity, which will be ideal because that's the clean source of energy? In 1821, Seebeck discovered if you have material B in contact with material A, and one of the junctions at temperature T1, the other one is temperature T2, it generates a voltage. The ratio of the voltage to temperature is what today we call Seebeck coefficient. And this is the basis of a thermocouple. That's how we measure temperatures. And this was, I guess, by accident. He was just doing some electrical measurement. He had a soldering iron or something next to one of the wires. He measured the voltage. What is interesting is that he was convinced that this is a magnetic effect. Why? Because he thought that will be a good explanation why Earth has magnetic field. Equator is much warmer than the north and the south poles. So he wanted to calculate the Earth magnetic field using the temperature difference. And he wasn't successful. I'm not sure if he had all the MATLAB fitting algorithm we had, he could find some relation there. So later on, people discovered that it's not a magnetic effect, pure electric effect. About 12, 13 years later, 1834, Peltier discovered a similar effect. If you take the same materials B and A in contact, but this time you send current through it, electrons go through the material. At one of the junction, heat is absorbed. In the other one, heat is released. And the ratio of heat absorbed or released to the current is what is called Peltier coefficient. So a way to think about this is that electron gas, as it moves, it takes energy, thermal energy from one point and move it to the other point. It sounds kind of related, but it took a while for people to realize. Another 20 years, Lord Kelvin or Thomson found that this Peltier coefficient is exactly like Seebeck coefficient time absolute temperature. And he used it, some general arguments of balances without knowing what is the microscopic origin of this, which is quite interesting. So this Peltier effect is used today. This is a commercial Peltier cooler or thermoelectric cooler that you can buy. It depends on the volume that you buy. It's anything from $5 to $10 to $20, $30. It's not very expensive. You send current. It's made of some materials that electrons go through it, take the heat from the top plate and move it to the bottom plate. These devices can cool by 72 degrees Celsius. Cooling power densities are low and efficiencies are low, about 6 to 8% of Carnot. So when you look at this, you say, that's a way I could convert current to cooling, a refrigerator, or the reverse project, I could convert temperature to a voltage. So that could be a possibility to generate electricity. And then what I have to do is that to use the best thermocouple I have in my lab and just use that for energy generation. And that doesn't work. That's because of non-ideal effects. This is the ideal effect, the voltage generated. But if you want to get power out of this device, a current should flow. If the material is highly resistive, all the energy is dissipated inside the thermocouple, and you don't get a benefit. That's one parasitic effect. The second parasitic effect is that I have a material, one side of it is hot, the other side of it is cold. Any material has thermal conductivity. It wants to transfer the heat from the hot to the cold junction, and that's a parasitic heat loss. So that also has to be minimized. So putting these two together, people found in 1950s that a single ratio of the material properties called Z determines the efficiency of the system for power generation and conversely for refrigeration. So let's see if we understand this Z parameter. Z parameter is the Seebeck coefficient squared times electrical conductivity divided by thermal conductivity. The higher is the Z, the better is the material for conversion of heat into electricity. Why? Well, Seebeck larger, you know, that's the effect of Peltier or Seebeck, both related proportional to Seebeck. Electrical conductivity is the parasitic Joule heat loss, and thermal conductivity is parasitic heat conduction. You want to make the material a very good conductor and a bad electrical conductor and a bad thermal conductor. So if you look at it, as you increase the temperature, efficiency of power generation increases. That increase is due to just simple Carnot factor. The larger is temperature difference, the more energy you can get out of your system. But Z times T become non-dimensional. This is dimension of 1 over temperature. If Z times T is about 1, you can have systems on the order of 8 to 10% efficient. That's what we are today. If this factor could be improved by a factor of 3 or 4, then we can get to 20, 30% efficiency. So that's what basically the whole engineering is about, how to improve the ratio of these three material parameters. What is interesting, and that's quite intriguing, is that each one of these material properties, you can change it at least by a factor of 10,000 to 100,000. You know electrical conductivity could be changed by doping. Thermal conductivity could be changed by alloying. And Seebeck, well, you don't have yet an intuition microscopically, but if you just look at tables, it could vary anything from a couple of microvolts per Kelvin to thousands of microvolt per Kelvin. So if you look at it, if each one of these could be changed by a factor of 10,000 easily, that should be a piece of cake to increase it by a factor of 3 or 4. And that was a business idea in 1950s. They spent more than $150 million. 60, 70 startup companies started. Don't think this is a 21st century phenomena. They wanted to replace all the refrigerators in the world because they said, well, if we have 6% efficiency right now, we go a factor of 3 better. That will solve all the problems, and you will have a quiet refrigerator. And a lot of people work on that. So that's never materialized. The person who was behind the early development of thermoelectricity was Abraham Yoffe, and I guess Yoffe Institute in Russia is after his name. During World War II, they built tens of thousands of these thermoelectric power generators to use heat sources from stoves and other things to operate radios. And a lot of people wanted to use that and expand it to a full refrigeration, and it never happened. Why is that? That's an interesting scientific question. If you look at this Z times T, which is non-dimensional, between 1950s when the first materials were introduced, and this parameter was about 1. And basically, year 2000, no changes. And what is interesting is that these are semiconductors that are the best materials for thermoelectrics. And at the time when thermoelectric research started, semiconductors for transistors were just picking up. So basically, transistors in the 50 years, they have gone 10, 12 orders of magnitude in improving information processing, but we haven't done anything on the energy conversion. One of the reasons, of course, first, I tell you, it's a difficult problem. The second is also energy was not our focus. It's that if you get cheap energy, then you don't put energy and effort in it. In the last 4 or 5 years, only in the last 4 or 5 years, we have seen cases where there have been significant improvements. This is, I guess, from our article from Arun Majumdar here. But only this was possible using nanostructured material, and I will discuss a little bit why we need nanostructures. But as soon as I show big jumps, I should warn you that that is also a good sign, but don't take it for granted. Superconductivity in 1984, you remember, that was a big jump in the transition temperature, suddenly at liquid nitrogen temperatures, and people thought that this could revolutionize the whole technological kind of way we do things to store energy, to transport energy, and so on, and this hasn't materialized. These effects are real, people measure it, but how to put it in practical applications is difficult. So thermoelectrics is not an exception. The two latest kind of major advances in the field happened just 4 or 5 years ago. Ted Harman and Rama Venkatasubramanian, they use this type of materials. These are quantum dot materials, and these are multi-layers superlattice kind of materials. In both cases, the material is engineered and the size scale of a couple of nanometers. Here is a case, they demonstrate one of these elements. Here is a heat sink, here is a thermocouple, and they basically made a refrigerator with it. And in this case, we also made small refrigerators on a chip. Both of these cases reported Z times T factor of 2 better than the state of the art. So you see that's a major breakthrough when you just change it by a factor of 2. So I will go into it, why this took so long and why this nanostructure was essential for improvement. But before I go into this, I want to tell you where today thermoelectrics are used. The conventional ones that were invented in 1950s, you can see them in beer coolers, small refrigerators or chocolate coolers. I haven't seen many of these around. But what is the basic idea is that mechanical refrigerators, they don't scale well at small sizes. When you make something smaller, mechanically, friction scales with the surface area and the cooling power scales with the volume. You lose on the volume to surface to volume ratio. And basically, the refrigerator is not as efficient. And that's why these are commercial areas. Big commercial market for thermoelectrics is in fiber optics. They actually can make little devices. Here is like a nail that are thermoelectric refrigerator that is this small, couple of millimeter square. And this could cool by 40, 50 degrees. And that's perfect for a laser diode, which kind of shown here. Basically, fiber optic communication has been very successful by sending lots of data, very fast rates over long distance. But even the most stable laser that we have, the distributed feedback laser, have a wavelength sensitivity that make it so that if you change the temperature of the laser by a couple of degrees, the whole fiber optic system will not work well. So each of these long-haul communication lasers is temperature stabilized to within a degree and is done using this small thermoelectric coolers. There is another area where thermoelectric power generation has been successful, is power in space. For a spacecraft that are close to Earth and going toward the sun, solar energy is a good option. But if you go farther away from the sun, solar energy is not enough. So Voyager spacecraft, Galileo, Ulysses, Cassini, all use radioisotope thermoelectric generators. What are these? These are little boxes. Inside of it, you have this hot red source, typically plutonium, something that's radioactive and creates heat on the order of 1,000 degrees. And outside of it, space is cold, 4 degrees Kelvin. So you have a large, good temperature difference. Between them, you put these small legs, which is shown here, which is based on silicon germanium. And that generates power on the order of 300 watts for a source which is 55 kilograms. And that works for many hours and many devices. Actually, Voyager spacecraft, the pictures we have seen that come from kind of end of the solar system, they all were powered using this type of devices. There's no moving part, and it just, well, you have to deal with plutonium, but it's in the space. Recently, there have been another area where thermoelectric have been very successful. Most of you have seen cars that have a car seat that could be heated. Now in luxury cars, you can get ones that could be cooled as well, and that's quite useful in places like Arizona when you can not sit in your car as soon as you turn it on. You have to wait. They have a little inside this car seat thermoelectric module that is a small refrigerator, and it circulates air and cools the seat quite fast. So you see, even though it's not an efficient system, for a very site-specific application, small scale is quite successful. This was first introduced in 2001 or so, and now they sell more than 1 million of these units per year. So that has been a good success. So we discussed a little bit about conventional thermoelectrics. Now I want to go into microscopic origin of this and see how we could engineer material properties. And that's also a good point to introduce what is the thermionic emission that I talk about. If we have a hot source in contact with a cold source, and we just having contact without anything in particular, you know what happens. You put a hot water and cold water in contact, well, you get not so hot, not so cold water. You cannot get energy out of it. To get energy out of a temperature difference, you have to do something. And here, if this is the energy axis, I put a potential barrier in a way that hot electrons could move, but not the cold electrons. As soon as I put the energy selectivity, then under a temperature difference, this device generates voltage. The effect when a potential barrier separates a cathode and anode, and only the hot electron are emitted, it's what happens in the cathode ray tube as well. In a kind of your old TVs now, you have a hot filament, and it's so hot enough that high energy electrons could come out. And people knew from a long time ago that this could be a source of energy. So in the case of a cathode ray tube, you have a low work function material, vacuum, and a low work function anode, and that could generate voltages. But typically materials, they don't emit electrons in the vacuum unless they are very hot. So this typically works on the order of 1,000 degrees Celsius or even higher, typically 1,500 degrees Celsius. If the temperature difference, which is lower, with what happens in your cars or a lot of low grade heat capacity, then the vacuum systems do not work. So you could use a semiconductor system or a metal where you can selectively put the materials with different band gaps and select between hot and cold electrons. And this could be used both for refrigeration and for energy generation. How this research was started was actually for information processing for silicon chips. We wanted to cool individual transistors. And here is the idea. Here's a silicon chip. On top of a chip, we grow 3 micron layers of some multi-layers. In this case, silicon, germanium, carbon, silicon. Layer thickness is on the order of 10 nanometer. This material system is chosen in a way that there is a potential barrier between these two materials. Hot electrons can easily move. Cold electrons cannot move. That's basically an evaporative cooler. You send hot and cold electrons to the top contact. Hot ones leave, cold ones stay there, and that cools the top junction. So this actually works. This is the couple of devices we built on a silicon substrate, and here is a thermal image of one of the devices. Current is sent to the middle device, and you can see the blue regions is cooled 4 degrees below ambient. And so basically, the heat is taken from this top surface and moved to the substrate. And this could have a very high cooling power densities, basically 10 times as much as what your Pentium dissipates on the average, and very fast. So that's where our research started, our information technology. And I guess the applications is that both for lasers and transistors, you have problems with heat. Can you locally heat individual transistors? The size of these refrigerators is about 40-50 micron. It's the size of a human hair. So it's really a very small refrigerator. So I guess it's an interesting story, because when we built first one of these, I got a call from somebody who said that I'm calling from World Guinness Book Hollywood, and we want to make a movie about your refrigerator. We heard that you made world's smallest refrigerator. I said, I haven't looked at what other people have done, but probably you cannot do anything mechanical that small. That's probably true. So she said, well, send me some photos of how it works, and we want to do a movie program, a small program based on it. And I sent these photos, and of course, students work hard to make a little animation. You send current, and you see how the heat is dissipated. And I got a call back saying, interesting. Where is the refrigerator? And I tried to point to her. This is where is the cold point. And she said, where is the refrigerator door? So that's a lesson. If you don't put a door for your refrigerator, you don't go to Hollywood. It wasn't interesting enough. They thought that we just took a real refrigerator that you have at home and just miniaturize it. So now let's look at more fundamentally. If we want to use this concept of energy filtering for improving energy efficiency, we have to overcome some fundamental material trade-offs. If you take any material which is conducting electricity and you put more and more electrons in it, typically the material conductivity goes up. You can have a better conductor. But the Seebeck coefficient, which is the coefficient that governs exchange of energy between heat and electricity, goes down. So S squared sigma, which is important for us, is typically optimum at certain intermediate range. This trade-off between Seebeck and conductivity is one of the major reasons people were not successful in the last 50 years to improve this parameter Z. Every time we made this one bigger, Seebeck went down, and material which is good electrical conductor is typically also a good thermoconductor, everything went bad. So we have to decouple these material parameters. So for those of you who have taken solid state physics, you can look at the right side, and for those who haven't taken, look at the left side. Basically, what can you do a metal? What is the problem with metals and semiconductors? In a metal, you have lots of electrons. This arrow shows how many electrons move. The red one is the hot electrons. Blue one is the cold electrons. In a metal, when you apply a voltage or a temperature difference, both hot and cold electrons move. There are lots of them, but they move by the same amount. You don't have a selection between them. That's what is the problem. In a semiconductor, when you apply a bias, hot and cold electrons move by different amount. And this difference is the exact definition of the Seebeck coefficient. And this is why this works. And picture here shows the density of states and the Fermi energy. So for those who have seen it, it's the same figure. But that's basically what is behind why metals are good electrical conductor. Lots of electrons move, but they don't have good Peltier effect. So what we could do is basically make a metal and then block one of the electrons. That's basically creating speed bumps for some of the electrons. And this should make a metal quite good. These are theoretical calculations, came out a couple of years ago. The Z times T we could get with a metal with high Fermi energy, high number of electrons, could be an order of magnitude better than the current state of the art. These are good theoretical results because they helped us to get a grant for a center. We are working in 7 universities, try to basically experimentally demonstrate that. And that also shows some of the tendencies now that you see in the technology. A lot of advances in fields happen in one specific area, material science, or in the devices, or in the physics. If you want to work in energy, you really have to consider the full system consideration. So we need to have people that understand the heat transfer part of it. We need mechanical engineers. So at UC Berkeley, Arun Majumdar is involved. We have Venki Narayanamurthy at Harvard, who is basically looking at the micro-scale, nano-scale electron transport, but the difference between hot and cold electrons. We do system-level testing at MIT, basically electrical engineering department. Material scientists at Purdue, UCSB, and NC State make different type of materials that are nanostructured, and then we characterize them. So the whole issue is really related to how we can make this material and improve it. So what is our kind of status after 3 years of research in this area? This is our best material. Looks like a material that has some disease. You see some black areas there. But this is a good disease. These black areas in the material are small nanoscale particles. This material is indium gallium arsenide, which is a common semiconductor. And inside of it, we have embedded erbium arsenide, which is a semimetal. The reason this is so hard to make such material is that if you do high resolution, these are acronyms here, is for some high resolution electron microscopy that could differentiate different atoms. You could see when you look at this material, you have these blue atoms, which is arsenic, which is perfect lattice. Everywhere is yellow, you see InGaAs. This is the semiconductor, and this red region is erbium arsenide. So we are able to basically put nanoparticles inside a semiconductor without creating defects in the lattice, without killing the electron transport. One thing these defects do is that they reduce thermal conductivity. This is actually measurements done here at UC Berkeley, which will Kim, Susan Singer, and Arun Majumdar's group. Bulk indium gallium arsenide, this is the thermal conductivity versus temperature. It's at room temperature about 6 watt per meter Kelvin. When you add these little nanoparticles to it, depending on how much percent you have and what combination, you can reduce the thermal conductivity easily by a factor of 3 or 4. This factor of 3 or 4 reduction in thermal conductivity is quite substantial because usually you can't reduce it that easily. But what is even more interesting is that the electrical conductivity or electron mobility is not significantly reduced, and the material conductivity is not significantly reduced. That's the key factor. So this is how to engineer two of the properties, electrical conductivity and the thermoconductivity. How about the third property, which is the Seebeck coefficient? In order to engineer the third property, we made multi-layers. These are InGaAs, indium gallium aluminum arsenide is made of these multi-layers. Basically, we want to block hot electrons. And this graph shows the Seebeck coefficient. This is the coefficient that characterizes exchange of energy between heat and electricity as a versus doping for 4 different samples, cross-plane and in-plane. So basically, when electrons move in this direction, they have a higher Seebeck coefficient when they move in this direction. That demonstrates that there is an electron filtering effect. Electrons, on the average, carry more entropy. And this material, room temperature ZTs are still 0.1, but theoretically, we think that we can get at ZTs more than 1 at high temperatures, and that's what we are working on. Let me skip these graphs. In order to do energy experiments, just demonstrating a material system is not enough. You have to build systems and do input-output analysis, and that was a big lesson for me. I used to work in optoelectronics. You had some ideas how to make a better laser. You just go in the lab and you try it, and then you didn't basically have to build the full fiber optic system to demonstrate that your idea was correct. Here, to do an energy in, energy out analysis, you have to build the whole system to demonstrate that the system works exactly as you expect. So these are the models that are fabricated at UC Santa Barbara, and it shows that at 100-degree temperature difference, we can generate on the order of a watt per centimeter square. So let me end with some, at least you see some animations. Microscopically, what happens when you put 2 electrodes in contact with each other. So here what you see is a highly doped region, lots of electrons on the right and the left, and I put them in contact, and as you see, electrons move from one side to the other side, but only, this is the energy axis, only electrons that have high energies. The low energy electrons, they can't go there. This little potential barrier that acts like a filter, that's the key thing that causes when, as electrons go from this layer to this layer, they actually take energy from this point and deposit it here. And this is typically what happens in a thermoelectric material as well. So if you remember, I mentioned 2 effects. Electrons move from material 1 to material 2, then to material 1. As a bulk effect or as an interface effect where you have cathode and anode and a barrier, both converge in the limit of large systems. At a small system, when electrons are ballistic, then you have differences. So if you take this and kind of analyze it, you see that, this is the energy exchange versus length. On one side of this thin half a micron layer, there is cooling. In the other side, there is heating. So let me just finish with a quick overview. I discuss about the problem of the waste heat, the way we generate electricity, and the way we operate our cars. Both of them produce lots of waste heat. These are low-quality waste heat. What I mean is that the temperature, if it's large, you can just evaporate water and just run a turbine. When it's small, that's not very economical. So then I discuss a possible way of using Seebeck and Peltier effects as a solid-state energy converter, show some of the applications, but really show that using nanoscale materials, when you can decouple the 3 material properties, Seebeck coefficient, electric conductivity, and thermoconductivity, that's only the time you can make a very good solid-state energy converter. Thanks for your attention.
This is working. Questions from the floor for 5 minutes or so. I think we're all shocked by such a brilliant presentation.
I slipped.
Yes. Thanks.
For example,
shy to start with. That's good.
Yeah, if you use a thermoelectric device to recover a waste heat, for example, like in power plant, what is the efficiency that you expect? What is the increase?
So I guess out of the heat that is dissipated, the question is that how much % of it you could recuperate and generate electricity. Current state-of-the-art material is 6-7%. So you calculate if I'm dissipating 50% of the energy, and out of that I get 6-7%, that's like 3% increase in the overall plant efficiency. Right now, well, 3% is not negligible. Right now, the problem is that it's not cost effective. You need a lot of materials. is a little like the solar cell argument, is that if the energy comes and you can just, if the material is cheap enough, you can put it in lots of areas, you can always generate electricity, but the issue is the cost effectiveness. With the ZTs that are currently, people have demonstrated, I think up to 20% should be feasible, and there are now applications where car companies are working to see if it's feasible, for example, to use the heat in the catalytic converter. But that's remained to be seen. And really widespread application could only happen when we reach 30–40% efficiencies, which require a lot of engineering.
Fantastic answer. Another question from the floor? Yes, let me give you the microphone. Oh, you go.
Can you say something about the space charge effect in the solid-state thermionic emitter?
In the case of vacuum, that's a good technical question. In the case of the vacuum devices, electrons are emitted from a solid inside vacuum. And even if you have a material with a small work function, as soon as they come out, the negative charge of the electrons in the vacuum creates a potential barrier for additional electrons to come out. So that's something that basically limits the working efficiencies of vacuum devices to more than 1,000 degrees Celsius. In the case of solid-state devices, we don't have that problem. The barriers are much thinner, so space charge effect is not the main factor. Our key factor is to have a material which is a good electrical conductor and bad thermoconductor.
It looks like we're at the end of the seminar, so I wanted to thank you all for coming. And as usual, let's give our speaker a fantastic round of applause. Thank you.